Welcome to today's webinar. The topic today is cross-section modeling and stress analysis in our section 1. My name is Andreas Hörold. I am responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today, and I will answer your questions during the webinar. Sonja will be the presenter, but she can introduce herself.
I would also like to welcome you to today's webinar. My name is Sonja von Bloh and I will be the presenter today.
Okay, thank you for your introduction. Then I switch off the webcam that the attendees can see the full screen. For the attendees who participate the first time or the first time with the new application, you can press that button in your menu, and then you can enter a question here. And with this wheel, you can adjust the audio settings if it is necessary. You can also watch the entire webinar and then email your questions and also to info@dlubal.com. To the agenda today. At first, Sonja will introduce the plastic resistance design, the implemented simplex method in our section. And then the following points are more tips and tricks. She will show you how you can connect elements and how you can generate subpanels, how you can consider openings in cross sections, and how you can modify elements. Okay, that should be all from my side. I hand over the screen to Sonja. Just a moment.
I would first like to show you how to determine the plastic cross-section resistance of general cross-sections. I would like to show the plastic analysis using an example. For this, I've already created a file. Here I go to the base data and I choose the analysis method. I choose here the finite element analysis, and then I activate the plastic capacity design according to the simplex method. Then I activate also the calculation of the effective cross-section, and here I choose the standard Eurocode 3. This is needed for the classification of the cross-section. Then I go to OK, and then I choose the material. The material S235 is already chosen. That's okay for me now. And then I add the corresponding cross-section. For this, I create a new section. Then I go to the database, and here I choose the build-up cross-section. And here I choose an I section with two side flat bars. The I section should be an IPE 200, and the flat bars should have a thickness of 8 millimeters. Then I click on OK. Then I have to create a load case. I do this here via the navigated data, new load case, and this is my design load case. Okay, and then I have to define the internal forces. Here I define a shear force about 500 kilonewton and a bending moment about 30 kilonewton meter. And then I start the calculation. Design using the plastic cross-section resistance is an essential aspect for efficient steel structures. Eurocode 3 provides solutions for combinations of internal forces only for specific cross-section shapes. The plastic cross-section resistance, considering various combinations of internal forces, can be determined in our section using the simplex method. The simplex method is an optimization procedure in which the cross-section is divided into numerous elements. Each element can have a value between the positive and negative yield stress and must fulfill the yield criterion. An optimization algorithm determines the stress distribution so that the inner and outer forces are in equilibrium. In addition to the variation of the normal stresses, you can simultaneously vary the shear stresses over the cross-sectional area. However, the plastic redistribution of shear stresses only takes place if the elements are defined as well. In this cross-section also elements are defined, so the redistribution of shear stresses takes place. If no elements are defined, the shear stresses are important from a previous elastic design. Thus, the shear stresses represent input parameters of the linear optimization, whereas the normal stresses are explicit variables for the optimization. According to Eurocode 3, the plastic cross-section resistance may be utilized for class 1 and class 2 cross-sections. First, you have to determine the cross-section class for the combination of internal forces to be analyzed. I've already for this activated the add-on effective cross-section calculation according to the Eurocode 3 so that the classification will be carried out. And I want to show you now the classification. For this, I choose here on the table the effective thin wall analysis, and here I choose the section classification, and here I can see this cross-section falls into class 1, so it's possible to do a plastic design. Then I want to check the elastic design, and to do this I open here the finite element analysis results, and I switch to the stresses. And here a stress, an equivalent stress according to von Mises is calculated about 280 Newton per square millimeter, and this results in a stress ratio over 1, so the design is not fulfilled. Then I want to see the plastic results, and for this I open here the table plastic capacity design, and then I look to the enlargement factor. On the plastic calculation, the enlargement factor alpha is determined. The enlargement factor implies that the plastic capacity of the section is attained if all internal forces and moments are uniformly multiplied with it. In the case of a factor greater than 1, I can increase the internal forces by this factor. In the case of a factor smaller than 1, the design is not fulfilled. The enlargement factor is here greater than 1, so the plastic design is fulfilled. Now I would also like to analyze which enlargement factor would result without the redistribution of shear stresses. This is the solution that is also implemented in shape thin. To do this, I explode the cross-section into its individual elements, and I choose here for this this option explode. and then I delete all elements. And then I go to the base data and I deactivate the calculation of the effective cross-section, because for the calculation of the effective cross-section, elements are necessary. And I click here on OK and I start the calculation. And then I look to the plastic capacity design results. And here the enlargement factor is less than 1. That means that the design is not fulfilled without the redistribution of the shear stresses. Then I want to go to the next topic of the webinar. I would like to explain to you when elements are connected to each other and how this connection can be created. Elements are connected if they share a common point. To explain this, I would like to show you a few examples. For this, I first create a new file, and I name this file example2, and I choose the analysis method, a thin-walled analysis. Then I click on OK. I create 2 elements first, and I do this via the graphical input. Here I choose a single element. I define a thickness about 10 millimeter, and then I create the first element and then the second element. I want to show also the numbering, and you can see here the element 1 has the points 1 and 2, and the element 2 has the points 2 and 7. Elements 1 and 2 are connected because they share the same point 2, that's here in the middle. I then want to show you another example where 2 elements cross each other. For this, I delete these elements, and I deactivate the option Auto Connect Lines and Elements, and I also deactivate the option Auto Split Elements. Then I create the first element, and then the second element that crosses the other element. The elements are not splitted in their intersection point because I've beforehand deactivated this option Auto Connect Lines and Elements. Therefore, I have only 2 elements, this element here above, and then this crossing elements. And the elements 1 has the points 1 and 2. The element 2 has the points 7 and 8. So they do not share the same points. Therefore, they are not connected. If I start the calculation, I get a plausibility check error that the part consists of several unconnected elements. If I want to create this connection, I can do this afterwards. For this, I choose here this function Connect Lines and Elements, and then I draw a rectangle over the intersection. And now you can see this element here above is splitted into 2 elements. You can see this also in the navigator data. And now all the 3 elements share the same point, and that's the point 8, and that's why the cross-section is connected. if I now start the calculation, I didn't get this plausibility warning anymore. Then I want to show another examples with two cross sections. For this, I delete the elements here, and then I insert a new section. And the first cross section is an UPN 200. I choose it here. And this cross-section is rotated about the x-axis about 90 degrees. And then I click here on OK. This cross-section will be inserted into my file. And then I create the second cross-section. I do this via the navigator data, new section. And this cross-section should be an IPE 200. I choose this cross-section, and I want to put this cross-section on this point on here, this location. And then I click on OK. The elements of cross-section 1 are not connected to the elements of cross-section 2, as they do not share any common points. If I want to create this connection, it's first necessary to divide the cross-sections into their individual objects. That means in their points, lines, elements, parts, and so on. This is necessary that you can edit the individual objects. To do this, I go to the navigator data, and then I select the two cross sections, and then I click here on explode. The connection can be created using an element, and for this I want to create a connection where the two cross sections are welded. This is here on this location and on this location. To do this, I create a new element, and I choose here a thickness about 0 millimeter, and I have to define the effective thickness for shear transfer, because the shear is transferred via the welds. And here I define a shear thickness that corresponds to the thickness of the weld, and that's 5 millimeter. Then I create here this connection. Now this element is not divided because here the outer connect lines and elements function is not activated. So I choose here this function again to connect lines and elements. So that here the connection will be created. Now this element, this web, is divided into 3 parts. Now I would like to go to the next topic of this webinar, and these are the subpanels. The subpanels are necessary for the classification and calculation of the effective cross-section. the subpanels are generated automatically based on the standard selected in the base data. Subpanels can only be generated if elements are defined as vals. The standards Eurocode 3 and Eurocode 9 only provide rules for the generation of subpanels for constant element thicknesses. Therefore, subpanels are only generated if the boundary lines of the part are equal to the element edges and if no other part is connected. I would like to show you how this is done using an example of a channel section, and for this I create a new file, example 3. Here I choose also the analysis method thin-walled analysis, and I activate the add-on effective steel section, and here I choose the standard Eurocode 3. Then I click on OK. And I insert then a channel section from the cross-section library. To do this, I open the library, new section, go to the library, choose here this channel section, and then I explode this channel section in its individual parts by this button. Now this channel section is splitted into its line, its part, and its element. And I want to check the subpanels. And here 3 subpanels are automatically generated based on the Eurocode 3. And these are the subpanels for the web and here for the flanges. If I now move here this point a little bit upwards, I will do this. Here maybe 10 millimeter, then the subpanel will be deleted. This is because the boundary lines of the part, that this is the boundary lines, is not equal to the element edges. And this is here the element edge, and this is because now the subpanels is not generated anymore. If I start the calculation, I will get a warning about this, that the element has no contact to the boundary. So the subpanel is not created. I can ignore this plausibility check warning, then the calculation is carried out, and the calculation, the classification and calculation of effective cross-section will be done, but only then for the parts where subpanels are defined. I want to show you also a next example where an I-beam is reinforced with a flat bar on the upper flange. And I create a new file for this. This is example 4. Here I choose also the analysis method thin-walled analysis, and I choose, or I activate the effective calculation of the cross-section properties, and I choose also the standard Eurocode 3. Here I deactivate the auto-connect lines and element function beforehand, because I don't want that the parts of the cross-section will be merged as one part. then I insert the cross sections. To do this, I go to the navigator data, open new section, and the first cross section is an AHB 200. And then I insert this cross section, and the second cross section is a flat bar, and I insert this also via the cross section library, new section, open the cross section library, go here to bars, and the width should be 160 millimeter and the thickness 10 millimeter. Then I go to the tab section location, and I want to put here this part on the upper flange, and then I click on OK. Then I explode the two cross sections into its individual objects. For this, I select the two cross sections, and then I choose here explode because I want to create the connection between the upper flange and the flat bar. To do this, I create an element with a 0 thickness for this, and I choose here the option single. Here I define a thickness about 0 millimeter. I have to define the effective thickness for shear transfer. This should be 5 millimeter. And I forgot, I wanted to activate the auto connect lines and elements beforehand. So I open the new element dialog once again and define here the thickness, and then I connect the two elements where the welds are located. Here on this side and on the other side. And now you can see that the subpanels are generated automatically. The subpanels are not created here in the location where the reinforcement is defined, where the flat bar lays on top of the flange. It's because the element edges correspond to the boundary lines of the respective parts, but the parts are directly adjacent to each other, so that no subpanels are created for the upper flange and for the flat bar. If I want to create subpanels for the flange and the flat bar, a distance between the parts with their elements has to be created. That's because I've deactivated before I explode the cross section into its individual part this option, because I wanted to have the two parts separately, so that I can now move this part a little bit upwards. To do this, I select the part and also the elements, and I choose then the move copy function, and I want to lift it a little bit upwards, about 1 millimeter in the negative direction. Therefore, I put a negative sign, and then I click on OK. Now I see that the subpanels are created here for the flange, but I can see that the subpanels are not created for the flat bar. The subpanel for the flat bar is not created because elements with thickness 0 are not considered when creating supports of the subpanels. You can see it also here. The element with 0 thickness is connected to this point, but this element with 0 thickness is not considered as a support, so therefore you don't have a support here on this location. If I want to have a support there, and if I want to have subpanels for the flat bar, it's necessary to create an element with a thickness bigger than 0. I want to do this now, and for this I delete the elements with 0 thickness beforehand. And then I create here a new element, and I define a thickness that's equal to the thickness of the weld. Now you can see that subpanel is now generated here for the flat bar, and here this subpanel is divided into 2 subpanels because now this element with a thickness bigger than 0 is considered as a support. If you only want to create a subpanel for the flange plus the flat bar, it's necessary to merge the parts and create only one element. I've already prepared that here. You can see this in this example. Here I've only created an element with a thickness that's corresponds to the thickness of the element of the flange plus the thickness of the element of the flat bar. And here only one subpanel is created. Now I'd like to move on to the next topic of this webinar. These are the openings. You can model openings such as bolt holes in our section. However, this is currently only possible for the thin walled analysis design method. I create a new file for this, and I call it example 5. I choose here the thin walled analysis, and then I click on OK. You can model the openings by using elements with a 0 thickness, since the cross-section has a hole only at this considered member location, and the complete cross-section before or after ensures the connection in the member. The cross-section is connected, and it's also possible to transfer the shear. Therefore, I have to define effective thickness for shear transfer. I will do this now. I want to create a channel section with a hole in its web. I choose here a new element define here the thickness of the flange. And then I create the flange, and then I create the element to the location where the hole is. And then I want to create the hole, and for this I define a thickness of 0 millimeter and define here a thickness for shear transfer about 10 millimeter. And then I create the other part of the web and then the upper flange. When calculating the stresses or the shear stresses, each zero element is fully considered with its effective thickness. Thus, the stresses on zero elements are displayed. I will show you this for the shear stress here. I choose here the type of display off, and you can see now here where the hole is located also shear stresses are calculated. The classification and calculation of the effective cross-section with holes is not described either in Eurocode 3 or Eurocode 9. Therefore, my recommendation for small bolt holes at connections is not to define them in the cross-section, but to define the local section reductions in the design add-ons, such as steel design. They can then be considered in the design checks. Bearing stresses cannot be calculated in member model either, so you should analyze a surface model. Finally, I would like to deal with modifying elements. For this, I create a new file. I name it example 6. I choose here the analysis method, thin wall analysis, and then I click on OK. Elements must always lie in a part, so that's necessary to create also a part. If you change elements, you must also adjust the corresponding part. It's necessary to adjust the part because the part is considered in most of the cross-section properties, such as the cross-section area or the moment of inertia, even when analyzing thin wall structures. I want to show you this on an example. Here I create a flat bar with a thickness of 20 millimeter. I use here the graphical input, and via the graphical input the elements are created and also the corresponding part. And here I choose a thickness about 20 millimeter, and then I create the element with a length of 100 millimeter. And you can see here the element is generated, but also here the part is generated. If I now start the calculation and I check here the sectional area, the program calculates a sectional area about 20 square centimeter. And if I now change the width or the thickness of the element, here I choose a thickness of 10 millimeter. You can see this in the graphic too. This is the element and this is the part. And if I start now the calculation, then also a sectional area about 20 square centimeter will be calculated. I also have to change the part so that the sectional area will be 10 square millimeter. I will do this here manually. I select here the lines and the points. I do this here on this side too. And now if I start the calculation, I get the desired result about 10 square centimeter. Adapting the part to the element is relatively complex, so I would like to show you an alternative approach to creating elements. A modification therefore requires less effort. To do this, I create the center lines of the cross section. I will do this here. And now I create here the center lines of a channel section. And I can then add a comment to the points and lines. With a comment like center line, I know that I can't delete this object if I want to keep the center lines. I will do this now. So I select here the lines and the points. And here I added now the points, and I define a comment center line for the point, and I will do this also for the lines. Click here on Edit, center line, and then I click on OK. And if I look into the navigator data, I can see also this comment here. You can then use the create elements online function to create elements and the part. I will show you this now. You find this function here in menu tools, modify elements, create elements on lines. I have to select the lines. They are already selected. This is because here the line numbers are in this field. And then I have to define the thickness. And then I click on OK. And now the elements and the part are created. If I now want to change the thickness of the elements, I change the automatically created points and elements. I delete them. I delete also all elements. And I now can add the elements again, create elements on lines. I have to select the lines. And here I define now the desired thickness. It's also possible to do these modifications via a script. I will show you this too. I create before the center lines. You see now no comments are added. And I've created a script that sets the comments. Double-clicking on the script will here run the script. And now the comment is added to the point and the lines. Then I create the elements on lines. I choose here the lines. Then I click on OK. And if I now want to delete the automatically generated elements and corresponding points and lines, I have created for this also a script that deletes these elements and lines. This brings me to the end of the webinar. I will now give the floor back to Andreas.
Okay, thank you, Sonja, for your presentation. I hand over the screen to mine. Just a moment. So you should see my screen. Before I will show you the website and to show you where you can find the recording and the models and so on, I would like to give you an offer. You can book your free online appointment anytime. For example, for a product demonstration. You can also ask for a non-binding offer of any of our products. Then just contact our sales team via that link, or you can also scan the QR code. So let me open the website, dlubal.com. Under News and Events, you find the events and then here the webinars. Those are the webinars of the next weeks. Next week, consideration of construction stages. Then the regular webinar about the most frequently asked questions. Then I will present this two-part webinar about the modeling and design of steel structures. The first part is, in my eyes, more for beginners, and the second part for beginners and profis. Okay, that's today's webinar. I click on it. In the next days, you will get an email with a direct link to that page, also with a link to the attendee certificate, and then you will find the recording in the middle here. You can already find the presentation slides, and if you scroll down, also the models, that you can go through the webinar. Okay, that should be also all from my side. Thank you for your attention. I hope we meet each other in the future webinar. Have a nice day and bye-bye.